I've been looking at problems from the oldest AMCs. AMC stands for American Mathematics Competitions. These have been sponsored by the Mathematical Association of America since the 1950s. Back then, they were called the ASME, or the American High School Math Exam. Most of the problems from these old exams are very similar to the ones that you'll see on a current AMC, but there were a few that were fairly different, and I have not seen anything like it on an AMC from the last 10 or 20 years. Let's take a look at some examples. Here's a problem from the 1951 American High School Mathematics exam. Which of the following statements is incorrect? Some statements are accepted without being proved. In some instances, there is more than one correct order in proving certain propositions. This seems correct. Every term in a proof must have been defined previously. This seems correct. It is not possible to arrive by correct reasoning at a true conclusion if in the given there is an untrue proposition. There's a lot of negatives in this statement, but I think this is true. An indirect proof can be used whenever there are two or more contrary propositions. I'm not familiar with the term indirect proof. I'm wondering if this is referring to proof by contradiction, as we often call it now. Let's take a look at the answer. The answer given in the book is statement C. Every term used in a proof must have been defined previously. This statement is incorrect. Some terms, which they call primitives, must necessarily remain undefined. I'm unfamiliar with this term, so I looked it up. In Wikipedia, it defines a primitive notion as a concept that is not defined in terms of previously defined concepts, motivated informally, usually by an appeal to intuition and everyday experience. Or they can be replaced by axioms. I'm familiar with the term axioms. You'll see these most often in Euclid's Elements. He begins with a list of postulates or axioms that we are to accept, and then from there we can prove a lot of theorems in geometry. Still, I think it's fair to say that a problem like this would not be found on a current AMC. We don't see this in a lot of math curricula anymore, including AOPS. If you have received this sort of instruction, I'd be interested in learning more. Please leave a comment if you've learned about something like this in school. Let's take a look at another example of a problem that you won't find on a current AMC. Some of the vocabulary from the 1950s has not really survived into the 21st century, and this is a good example. I don't think you'll be able to solve this geometry problem unless you know what an apothem is. I looked this up in an AOPS textbook. This is what I found. The apothem is the distance from the center of a regular polygon to the side. Even in AOPS, they refer to it as an obscure name, and you're definitely not going to see it on a current AMC without at least a definition. Let's try to solve the problem anyway. So we have the apothem of a square. It's the distance from the center of the square to the side. So I'll draw this perpendicular and we'll call this length d. Since we're interested in the area and the perimeter of the square, let's express the side length in terms of d. So the side length is 2d. The area is 4d squared and the perimeter is 8d. Dividing both sides by 4d, we get d is equal to 2. Let's now draw our equilateral triangle. I'll call the center O, and drawing this perpendicular to the side is H. We'll let the length of this apothem be E. Since this is a 30, 60, 90 triangle, the distance from H to C is E root 3. Triangle AHC is also 30, 60, 90. So this height AH is E root 3 times the square root of 3, which is 3e. Again, the area is equal to the perimeter. The area is going to be half of the base, which is E root 3, times the height, which is 3 times E. The side length of our triangle then is 2e times the square root of 3. So our perimeter is 3 times that. We'll divide both sides by E root 3, and we have 3e is equal to 6 and e is equal to 2. We're asked to compare the first apothem, which is the apothem of the square, to the second. It looks like our two apothems d and e are both equal to 2, so our answer is A. Let's take a look at another problem. This problem is from the 1952 OSME. I don't think you'll see a problem like this in any current AMC because I don't think very many students know what a powderman is. I'm not even really sure what a powderman is, except I can guess from the problem statement. It sounds like a person who sets up some kind of explosive, lights the fuse, and runs away. In this problem, this is what I picture. We have our powder man here, and he's just lit the fuse to light this explosive. It says in the problem statement he ran away at this speed. I think in a current AMC problem, they'll be careful to say that immediately after he's done lighting the fuse, he immediately starts to run. And then 30 seconds later, we have the explosion, and our powder man now is some distance away. He's been running for 30 seconds at a rate of 8 yards per second. So let's calculate this distance. This is 240 yards. The explosion causes these sound waves now that are going to pursue the powder man. The sound waves travel at 1,080 feet per second. The man is traveling at 8 yards per second, or 24 feet per second. So every second, the sound waves gain on the powder man by 1,056 feet per second. 30 seconds after the explosion, the man has traveled 720 feet. We'll divide this by 1,056 feet per second, and it takes 15 over 22 seconds for the sound wave to catch up with the man. Looking at the problem statement, it says when the powder man heard the blast, he had been running for how many yards? So I suppose we need to include those first 30 seconds. It'll be the 30 seconds after he set the fuse, plus the 15 over 22 seconds that the sound waves take to catch up to him. We'll add these two and see if they're close to any of the given answers. Multiplying and simplifying, this is 2,700 divided by 11. If you want to be accurate, you can do the long division. And our quotient is 245 with a remainder of 5. Let's check our answer choices. This is answer choice D, but what we also notice is that the answer choices are not given in a sorted order. I'm pretty sure on a current AMC, you're going to see the answer choices in increasing order, so you don't have to go back and forth and figure out which answer choice is closest to the one you calculated. Let's take a look at our last example. When I first read this problem, I was a little surprised because it was the first time I had seen a problem referring to any women or girls in any of the problem statements. I went back to double check, and this is not an exaggeration. Here's a typical page of problems from a 1955 OSME. Anytime a person is named, they are given a male name. It seems like girls would be just as likely to play marbles as boys, or something else that's countable. But in every problem I've seen in the 1950s, I've only seen boys or men, male names, or a Mr., and I never saw a girl's name, which is why it was surprising for me to see a reference to women and girls in this particular problem statement. Let's solve it. Let's say that the value of the estate is 2 times n. This allows us to avoid fractions since we're going to allocate half of the estate to the daughter. The ratio of the amounts received by the son, the wife, and the daughter are 1 to 2 to 4/3. Let's make this a little easier on ourselves by multiplying this ratio through by 3. So if the son has some multiple of 3, like 3x, then the daughter's portion of the estate is 4x, and the wife's portion of the estate is twice that much, 6x. The son and the daughter got half of the estate, that's 7x. The son, the daughter, and the wife received the entire estate except for the $500 that went to the cook. So we have 13x on the left, and we'll substitute for 2m, 14x, and solve for x. This means the son received $1,500, the daughter got $2,000, and the wife received $3,000, for a total of $6,500. Then we add to that the $500 that went to the cook, and the total estate is $7,000. That's answer choice D. Another thing that's unusual about this problem is that it's numbered 28. A current AMC has 25 questions, but an OSME from the 1950s has 50 questions, although I haven't been able to figure out how much time was allotted to solve these problems. If you have any questions about any math contest problems, please leave them in the comments.